Okay, so for this video, we've got quite a bit to cover. And the first thing we're going to do is talk about the initial conditions for a simple harmonic oscillator. Okay, because one of the interesting parts of a simple harmonic oscillator is when we came up with this equation, okay, that A cosine angular frequency times time, okay, that only accounts for a graph that looks like a cosine graph. Okay, but there's no, that means the object started out at the amplitude, but there's nothing saying that the object has to start at the amplitude. Okay, if you consider this graph, okay, this would mean that the object, when we started taking our time, it did not start at the amplitude, which would make it a cosine function, and it also did not start at equilibrium, which would make it a sine function. Okay, so we have to have a way to compensate for that. Okay, so to do so, let's look at circular motion, because in a lot of ways, circular motion emulates exactly what we see with a simple harmonic oscillator. Okay, so if you look at this picture, we drew a circle, and underneath I'm going to draw a box on a spring that's oscillating between the points of the amplitude and the negative amplitude. You'll notice the amplitudes line up with both the positive and negative side of the circle. Now suppose this box moves in a little bit to the left. That would be equivalent to a particle in a circle going counterclockwise some arc length along the circle. Likewise, if you were on the negative amplitude and it was moving to the right, it would be moving counterclockwise on the lower half of the circle. Okay, so basically what this comes down to is that an object in circular motion, okay, is identical to a simple harmonic oscillator. So if we looked at the position of say the yellow dot, okay, we would have to look at the right triangle. Okay, it's a tiny little space here, and we would try to find, well, what is that x position? Now, when it was all the way out at the right side, we already said this was a position of the amplitude, so that means the hypotenuse of that triangle is the amplitude. That means that the x distance, where the yellow dot is, would be the amplitude times the cosine of the angle. Okay, and the way we got the angle was the particle was moving around the circle at a certain angular frequency for a certain amount of time. So if we plug that expression into this x equation, we get the same equation we got for a harmonic oscillator. So it shows that for a particle moving in a circle, its x position is equivalent to a oscillator. Okay, but now what if we didn't start at the amplitude? So we'll do the circle again, and this time we're going to say that the particle starts somewhere on the circle at some initial angle, so we'll just call it theta 0. Now, sometime later, the particle gets to a new angular position, okay, and it got there with some angular frequency over some time. So to find the new angular position, it would just be the angular frequency times time plus the initial angular position we started at. And that's just simply the kinematics of angular quantities. Now the theta 0, our initial starting angle, this is referred to as the phase constant. Okay, it's telling us the initial condition of our phase, and the phase is essentially this entire equation. Okay, so we can therefore write the position equation as the amplitude times the cosine of our phase, which if we're wherever we start, if for a generic starting point, that phase is the angular frequency times the time plus our phase constant. And this gives us a more general expression for how to find the position of a particle both on the edge of a circle and for a harmonic oscillator. So to understand some ideas of what the phase constant represents, well, consider that if the oscillator were to begin, so at time t equals 0, it begins at the amplitude position. Okay, then our phase angle, or phase constant, would be 0. And therefore our position equation would simply be a cosine of the angular frequency times time. That's what we already knew because we already assumed starting at amplitude. But what if we started somewhere else? Suppose we started taking measurements at the equilibrium point. Okay, so x is 0 when t is 0. And to add a little bit more to this, we're going to say that it's moving towards the left. Okay, now the best way to do this would be to look at the graph first. So if we're starting at equilibrium and we're moving left, we'd get a graph that looks like this. Now, this is essentially just a negative sine curve. Okay, so does that mean we change our equations to be a sine of the angular frequency times time? And the answer is no, because if we stick with our cosine function, but we choose the correct phase angle, which, as it turns out, if you have a phase shift or phase constant of pi over 2 radians, that turns the cosine function into a sine function. And more specifically, if it's a phase constant of positive pi over 2 radians, then it changes it to a negative sign. If it were negative pi over 2, it would change it to a positive sign. So our general equation for this oscillator then would be a cosine of angular frequency times time plus pi over 2 as our phase constant. And so that's what we mean by the initial conditions. Okay, and those are typically either given to you in the problem or something you'd solve for based on other numbers. Okay, so for our next part, we're looking at the dynamics of a simple harmonic oscillator. So dynamics means we have to look at the net forces. Now, there's a couple things we can do first. Starting with our position equation, we know how to get all of the kinematic quantities. The velocity, which is the derivative of position, we did this already, so it would be negative a times the angular frequency times the sine of our phase. But if we want to find the acceleration, okay, again, we know that the acceleration would be the derivative of the velocity, which you can also see is the second derivative of the position. Okay, and when we take this derivative, the negative sign stays, amplitude's there, but another angular frequency term comes out. So you'd have an angular frequency squared term now, and the sine turns back into cosine. Okay, now if you look at this expression, the a and the cosine function is the exact same product for our position equation x. That means the acceleration then is directly proportional to the position function, and it's proportional by a constant of negative of the square of the angular frequency. Okay, and now that's if we did this the kinematics way with derivatives. We could do this again if we look at just forces. So consider the box on the spring. It's somewhere to the right of equilibrium, which means there's a spring force trying to pull it back to equilibrium. Now that spring force is going to be remember Hooke's law, so it would be negative kx. And since that's the only force acting on it, that's equal to mass times the acceleration. Now, if we solve for acceleration, we'll divide both sides by m. Okay? And if you recall, k over m is actually the square of the angular frequency. Okay, so that means if we make a substitution here, we end up with an expression that says the negative of the square of the angular frequency times the position x is equal to the acceleration, which of course is the exact same expression we just got using derivatives in kinematics. So with confidence, we can see that the acceleration of an oscillator is proportional to its position by a constant of the negative of the angular square of the angular frequency. Okay, so that gives us some ideas of what the terms are, but let's do this another step. Okay, so while we look at the dynamics, let's look at it again, only this time we're going to look at it in differential form. Okay, so if we start with our net force, which was the spring force, Hooke's law, and we do the same process, we get rid of the m, so divide both sides by m, but instead of leaving this as just a, let's put it in differential form. Okay, it's actually the second derivative of position. So now everything has an x on it. Now, just to clean this up, typically what you'll see is if I set all this equal to 0, which means I add the k over m x term to the other side, okay, what we get is an expression known as the equation of motion. Okay, and that's very important because in a lot of free response questions for the AP exam, it wants you to write this, write Newton's second law or write the equation for an oscillator. Really, it could ask you this for any type of motion. It wants to know the equation of motion. Essentially, that means we're looking for Newton's second law in differential form. In this case, it's a second order differential equation. Okay, and by second order, we mean that not only do you have the function x in that equation, but you also have the second derivative of that function. That's why it's called a second order. Okay, now if you want to know how to solve this equation, it wouldn't be with typical integration methods. I highly recommend you look in the book to see how the author describes how to solve this. Okay, but one of the important things that you need to see from this is that whenever you have this equation of motion, okay, whatever the term is that's attached to x, or whatever our main function term is, that expression is always equal to the square of the angular frequency. Okay, and that's important. In the next video, we're going to talk about pendulums, and you'll see why that's an important thing to remember. The term attached to the x is always the square of the angular frequency. Okay, let's look at one more thing, and that's vertical oscillations. Okay, now we've already done put a box on a spring, pull it out to the left or right, and watch it bounce left and right. But a vertical oscillation, meaning you take a mass and hang it from the ceiling and just let it oscillate up and down, we're just going to show that it's actually the exact same result if it was horizontal. Okay, so let's imagine a box that's attached to a spring that's attached to the ceiling. Okay, and we pull this mass down some distance from the spring's unstretched length. Now that's important. Okay, we're talking about if nothing was attached to the spring, it has a certain length, and we attach a box and we pull the box down some distance y. That means there's a spring force, Hooke's law, equal to ky, minus the gravity trying to pull it down, and that equals mass times acceleration. So that's our equation of motion. Now, before we did this, we need to know where the equilibrium of the box and spring are. So if I were to put the box on the spring and let it come to rest, it stretches the spring some distance from the string's unstretched length. So let's call that y0. Okay, so y0 represents the distance that the box spring equilibrium is from the spring's unstretched length. Okay, that means that if we apply Hooke's law and the Newton's second law again, okay, we're going to get an expression that says that the spring constant times y0, okay, minus the gravity is equal to 0, because this is the equilibrium of the mass spring system. Okay, that means in our picture above, when we said that we pulled this box down a distance y from the spring's unstretched length, that means that our variable y, the distance we've stretched it, is really a combination of two things. It's a combination of the y0, where the box spring equilibrium is, plus the extra distance we pulled it below that equilibrium, which let's just call it y1. Okay, but the extra distance, y1, that's the distance we pulled it underneath the box spring equilibrium. Okay, that means y1 is essentially the amplitude of our oscillating system. Because if y0 is where the box and spring are in equilibrium, if I pull it down y1, it won't go lower than y1, and it won't go higher than y1 above equilibrium. So that makes y1 our amplitude for this oscillator. Okay, so that if I substitute that in for y, you get y0 plus y1. Now what I'm going to do first is I'm going to distribute the k to both y0 and y1. Okay, but then I'm going to reassociate the terms. So if I've got ky0, and then I bring the mg to that, and isolate those terms, then I have a ky1 left over. The ky0 minus mg, well, that was our equation to find the new equilibrium of the system. Okay, so that means that that term, ky0 minus mg, is actually equal to 0. So then our equation, what we're left with, is the spring constant times the amplitude of our oscillator is equal to the mass times the acceleration. And that equation was the exact same equation we used when we developed our equations for a horizontal oscillator. Okay, so all of that was just to prove that a vertical oscillator has the exact same equations for motion as a horizontal oscillator. Okay. All right, so that's really it for these videos in terms of how we're describing oscillating motion. So the next video is going to talk about some applications to that.